Welcome back, folks. We're continuing on with our short series of videos on basic maths. Let's see what we did the last couple of videos. We covered essentially 5 or 6 different points. The first of these was BADMAS, the order you do arithmetic operations in. Then we looked at column addition, subtraction, and multiplication. Point 5 was hugely important. Please learn your times tables. You can't do any kind of maths if you don't know your times tables well. And then finally, in the last video, we looked at a method of doing long division. Today, I want to talk about quadratic equations, a very important topic. For example, if you take a tennis ball and you throw it in the air, the trajectory it traces out is a parabola, which is an example of a quadratic equation. They are everywhere in real life. And at school, one of the skills you need to learn is how to solve quadratic equations properly. Before I look at some examples, let's first of all see the general form of a quadratic equation. They tend to look like the following. ax squared plus bx plus c equals 0. Here, a, b, and c are the coefficients, and x is the unknown that you're trying to solve for. To make life interesting, we'll assume that the leading coefficient a is not equal to 0. Otherwise, we're just looking at straight lines again. Okay, then, I want to manipulate the quadratic on the left-hand side, put it into a slightly different form. So I'm going to have a bit of a play around initially. If I write out the left-hand side, I have ax squared plus bx plus c, which I can rewrite as a times x squared plus b over ax plus c. What I want to do now is write the term in brackets here as something all squared. So I need to figure out what is the something that I need to square here. So I claim it's the following. I claim it's x plus b over 2a all squared that I need to compute the square of. Let's have a go. So this is x squared plus b over 2a times x plus itself gives me b over a times x. And then on the end, I have b squared over 2a all squared, which is 4a squared. But remember, we are multiplying this by a on the left. So I want to take a times the term in brackets and see what I get. I get ax squared plus bx. And then I get a divided by 4a squared. That gives me b squared over 4a on the end. So if I use this as my squared term, I need to subtract off this bit here, otherwise I won't get the correct right-hand side. So I have to take away b squared over 4a for this equation to make sense. Very important, please don't forget the plus c on the end of the equation. Now this is all equal to 0. So if I'm solving my quadratic equals 0, it's equivalent to solving this last equation down here, which is in a much nicer form, in my opinion. Let's rewrite it slightly. So in other words, if I take this term, this constant term to the right-hand side, what I'll end up with is a times x plus b over 2a all squared on the left-hand side equals on the right-hand side, well, let's see, it'll be b squared over 4a and then subtract c, but I can write c as minus 4ac divided by 4a. So I'm just manipulating this expression to put it into a nicer form. Now, if I divide through both sides of this equation by a, on the left-hand side, I'll get x plus b over 2a all squared. On the right-hand side, I'll get b squared minus 4ac divided by 4a all squared. But 4a squared is the same thing as 2a all squared in brackets. So that's equivalent to 2a all squared. Last thing to do is to take the square root of both sides. Let's do that. So taking the square root of both sides of my equation, on the left-hand side, I'll get x plus b over 2a. On the right-hand side, I'll get the square root of b squared minus 4ac divided by square root of 2a squared is just 2a. Huh. Is that completely correct? Have I missed a trick here? By taking the square root, on the right-hand side, I'm getting a particular number. But if I had minus that number and I squared it, I'd still get the same value on the right-hand side. So you have two choices, plus the right-hand side or minus the right-hand side. When you square both of those, you get the same thing. So here I should just tinker with my formula very slightly. Most of it's correct, but I'm missing one of my solutions. So I should put a plus or minus in here to indicate that when you take the square root, you've got two options, either plus this quantity or instead minus this quantity. What's my conclusion from all of this? In other words, what have we shown? Going back to our original equation, we were looking at ax squared plus bx plus c equals 0. We were trying to find the roots of this equation. Well, we've found them now. The roots are as follows. X equals, take this guy to the right-hand side, minus b over 2a, plus or minus the square root of b squared minus 4ac over 2a. This is commonly known as the quadratic formula. It probably deserves to be put in a little box. It's super useful. It allows you to compute the roots of a quadratic equation in general form. Just as an aside, the number that goes in the square root part of this formula, we call that the discriminant. So just a bit of notation, we call delta, which is the number b squared minus 4ac, this is the discriminant of your quadratic. We're certainly going to refer back to this in a little bit. So just to reiterate, at school, when people quote the quadratic formula at you, they mean precisely the formula for the roots of this quadratic equation. If your equation has this form here, then this is a quick and dirty way of finding the roots of your equation. So you compute both numbers on the right-hand side. They are the two roots of the equation. Of course, they could just be a single root if the discriminant is equal to 0. Let's try out an exercise. Why don't we look at the following problem? I'll give you a particular quadratic equation. In this case, 2x squared minus x minus 21 equals 0. can we find all of the solutions, all of the roots of this equation? Well, here I'd suggest using the quadratic formula. So using the quadratic formula, let me just remind you of it. The quadratic formula was this expression here, minus b plus or minus the square root of the discriminant divided by 2a. At this point, I need to plug in some numbers. So here, a is equal to 2, b is equal to minus 1, c is equal to minus 21. So if I substitute in these values, I'll get minus b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So 2 times 2. Now we need to work this out. Minus minus 1 is plus 1, so that's 1. Plus or minus, let's see what goes in the brackets. Minus 1 all squared is 1. Then I have minus minus gives me plus, so plus 8 times 21. So 2 21s are 42, 2 42s are 84, 2 84s are 168. 168 plus 1 on the end gives me 169. Divided by 2 times 2, which is obviously 4. Do you guys know your 13 times table? Fortunately, I do. I know that 13 times 13 is actually equal to 169. So in the brackets, I have 13 squared under the square root sign. So if you take the square root of 13 squared, you'll get 13 back out. So this simplifies. This is 1 plus or minus 13 divided by 4. So you're going to get two solutions here. If it's minus, you'll get 1 minus 13 is minus 12. Minus 12 divided by 4 gives you minus 3. Or the other possibility is it's plus. 1 plus 13 is 14. 14 divided by 4, that's the same as 7 divided by 2. You see how easy the quadratic formula is? The quadratic formula gives you the roots on a platter. All you have to do is take the coefficients of your quadratic equation, bung them in the formula, and out pop the two roots of the equation. This also tells you something interesting about the factorization of your quadratic. So let's remember what our quadratic was. We were looking at the following: 2x squared minus x minus 21. We've found the two roots, so we can write this as x minus minus 3, our first root, times x minus 7 over 2, which is our second root, times something on the end. Well, I know what the something on the end has to be, because if you take this bracket and you multiply it by this bracket, you're going to get an x squared coming out. So I need that question mark times x squared is equal to 2x squared on the left-hand side. So my question mark here must actually just be equal to 2. So if you work that out further, that's 2 times x plus 3 times x minus 7 over 2. And if you prefer, it looks a bit nicer if you take the 2 inside here. That gives you x plus 3 times 2x minus 7. What we've done here is to completely factorize our quadratic equation. So we've written our degree 2 polynomial as a linear polynomial times another linear polynomial. In this case, our linear terms were x plus 3 and 2x minus 7. That's one way you can factorize a quadratic equation. I want to give you a second approach that is sometimes very useful if you don't feel like using the quadratic formula. So my alternative approach would be the following. We'll take the same equation again, and we're going to guess what the right-hand side should look like. So let's guess the following form of it. How should I write this? We guess that our quadratic is something of the form 2x plus a times x plus b. I'm writing a and b in capitals to distinguish them from little a, little b, and little c. Now I know it has to be 2x plus something times x plus something because the term on the left-hand side is 2x squared. I don't know what capital A is, and I don't know what capital B is. I've got to find out what they are. Let's expand the right-hand side. I'll get 2x squared plus ax plus 2bx plus ab. And if you clean that up a bit, that gives you 2x squared. Collect together the linear terms, a plus 2b times x, and then on the end you have the constant term ab. Now I know something else. I know that ab has to correspond to minus 21. And likewise, I know that this coefficient here, a plus 2b, has to be equal to minus 1. So that gives me a pair of equations in A and B. Let's write that out. So if we equate both sides, we can say the following. AB has to be minus 21, and also A plus 2B has to be equal to minus 1. This first part is quite important. AB equals minus 21. What we've got is the following. We've got an integer times an integer equals minus 21. So each of capital A and capital B have to divide into minus 21, and their product has to equal minus 21. So I'm essentially asking, what numbers divide into minus 21? There shouldn't be that many of them. Let's see if we can write them down. So question, what are the divisors of 21? Oops. What are the numbers that divide into 21? Well, they come from a very select list. There's only essentially 8 of them. You could have plus or minus 1. You could have plus or minus 3. You could have plus or minus 7. And lastly, you could have plus or minus 21. These 8 possibilities, they are the only whole numbers, the only integers that divide into 21. So that gives us the possibilities for capital A and capital B. So we're going to do a little trial run. We're going to trial each of these possibilities and see what we get. So let's start with the first one. So if A is equal to plus 1, we're going to get 2x plus 1 times x plus b. Well, if A is equal to plus 1, B has to be minus 21. So that could certainly occur as a left-hand side. Let's work it out. That's 2x squared minus 41x minus 21. That doesn't agree with our quadratic equation up there. So our first attempt didn't work. Never mind, let's try again. I could have, instead of 2x plus 1, I could have 2x minus 1, in which case capital B has to be plus 21. So if you multiply that out, you get 2x squared plus 41x minus 21. Doesn't work. What else could we have? We could have capital A equal to plus 3. If capital A is plus 3, then capital B has to be minus 7. Multiply that out, see what you get. You get 2x squared minus 11x minus 21. How does that compare? Nope, that doesn't work. They have 2x minus 3, x plus 7. Here we get 2x squared plus 11x minus 21. No joy there either. It's looking a little forlorn at the moment, I have to say. You could have capital A equal to plus 7, in which case capital B has to be minus 3. Here we get 2x squared plus x minus 21. Actually, that's pretty close. We're within a gnat's whisker of getting our quadratic. Here we have a minus x. Here we have a plus x, but everything else agrees. So I reckon we're very, very warm now. Let's take capital A equal to minus 7. Capital B has to be plus 3. Multiply that out. We get 2x squared minus x minus 21. Eureka. Now we're cooking with gas. That agrees with our quadratic up here. So by a process of elimination, this sort of guess and try approach, we know that capital A times capital B is minus 21. That pins down the values you can have for A and B to a very, very small set, and then you just cycle through until you strike oil, essentially, or you strike gold would be a better thing. Cool. So we've got the correct formulation now. We've factorized our quadratic equation very nicely. So our conclusion step here would be just to summarize what it is we've actually shown. So we've shown the following. This equation over here, because we've factorized it as 2x minus 7 times x plus 3, the right-hand side of this is equal to 0 when 2x equals 7, or alternatively, x equals minus 3. If you prefer, you can write it in terms of x purely. That would be x equals 7 over 2, or x equals minus 3. Those are the two roots of your quadratic. Whilst I'm someone who likes just to give you single approaches, I think in this instance, having multiple approaches is a good idea. Okay then, let's have a think about it. I'll give you one more of these problems, and then we'll see what we can do. Let's look at a slightly different quadratic, namely x squared minus 4x plus 13 equals 0. Again, we're trying to solve it, so we need to use our friend the quadratic formula again. Let me just remind you what the quadratic formula is. If you want to solve this guy up here, it's x equals minus b plus or minus the square root of the discriminant over 2a. Again, we're just plugging in numbers from above. A is plus 1, B is -4, C is equal to 13. So using our only tool, what do we get? X is minus B, so that's -4, plus or minus the square root of B squared, which is -4 all squared, -4 times A times C, divided by 2A, which is 2 times 1. That simplifies. -4 is +4, plus or minus, work out this guy. 4 4s are 16. 4 13s, goodness, that's 52. We've got square root of 16 minus 52, all divided by 2. (16 minus 52 is -36, so we've got 4 plus or minus square root of -36 over 2. And if you take out the 6 from here, because this is 6 squared, you'll get 2 plus or minus 6 over 2 times root -1, which is 2 plus or minus 3 times the square root of -1. No problems, right? That seems fine. Or is it? What's the square root of -1? Yikes. So we've taken our quadratic formula, we've blindly plugged in numbers, and suddenly the quadratic formula has given us a number that we've never seen in real life before. So, warning, I don't know what to say here. Warning, square root of -1, exclamation mark, exclamation mark, exclamation mark. You can add your own expletives if you want. It's not what these videos are about. I mean, I know what one chocolate biscuit looks like. I know what several chocolate biscuits look like. I even know what a negative number of chocolate biscuits look like, because if I start eating them, I'm reducing the number of chocolate biscuits. I know what a half or a third of a chocolate biscuit looks like. I can just take a bite out of it. But I'm blowed if I know what the square root of -1 chocolate biscuits looks like. This is something very weird if you see it for the first time. So how can I describe this? If you like your horror movies, this is sort of the moment where your castle is struck by lightning. Think of it this way. Dr. Frankenstein is stuck in his laboratory and he's trying to, instead of reanimating a cadaver, he's actually trying to create a crazy number in his laboratory. He's creating the square root of -1. Can such a number exist? Well, I defy you to plug any number into your calculator and square it and obtain -1. It just ain't going to happen. Mathematicians have kittens worrying about these kinds of things. In fact, you can make sense of the square root of -1. There's multiple approaches. It's a really valuable tool. Some people call it I, i.e. mathematicians call it I. Engineers call it J. The reason why engineers call it something different is because they like to use I for the current in an electrical circuit, and that conflicts with the square root of -1. Which is the correct choice? It doesn't matter. As long as you're consistent, that's the main thing. So sometimes your quadratic equation will have the square root of a negative number in it when you apply the quadratic formula. In that situation, you have what are called complex roots, but no real roots. So let me just remind you what the discriminant of a quadratic equation is. We've seen it before. The discriminant is this number b squared minus 4ac. So if b squared minus 4ac is positive, your quadratic equation has two solutions. If it's negative, you have no real solutions, but two complex solutions. If it's equal to 0, you have a unique solution. So I can show you via a picture what's going on. If this number delta is positive, your parabola cuts the x-axis at two separate points. If it's negative, i.e. the yellow parabola, it doesn't pass through the x-axis at all. So you have no real solutions, but two complex solutions. And then the sort of tipping point case is when it just grazes the x-axis. That's when your quadratic equation has a multiple root. Don't knock the square root of -1. It's a wonderful thing, although it's not as wonderful as chocolate biscuits.